In this video, I want to quickly run through 5 relatively short examples involving limits of quotients and how most of these relate to L'Hopital's rule. We'll look at exercises numbers 16, 22, 24, and 26 from the textbook, as well as another example here involving hyperbolic functions. So starting with number 16, we have the limit as x approaches 0 of x squared divided by 1 minus cosine x. We usually want to try these things first by considering direct substitution. So we consider what happens if we plug in 0. Of course, we get 0 in the numerator. The cosine of 0 is 1, 1 minus 1 is 0. So the basic form of this is 0 over 0. This is an indeterminate form. This tells us a couple of things. First, direct substitution won't give us the answer. And second, the limit may or may not exist. And we'll have to do some sort of manipulations to figure that out. Now, before we jump straight to L'Hopital's rule, which will apply here because this 0 over 0 is one of the standard indeterminate forms that it works on, we should take a moment to consider whether there is an easier way to evaluate this limit. If we think about some of our trigonometric limits, we might realize, hey, if we divide numerator and denominator by x, so that in the numerator we'll be left with x, and the denominator will have 1 minus cosine x over x, and you think about this expression as x is approaching 0, well, this in the denominator, as x approaches 0, approaches 0. So we still have a 0 over 0 form. So unfortunately, in this case, even using our trigonometric limits will not help us. So it's time to go ahead and try L'Hopital's rule, see if that works. So I'll mark that with a little H for L'Hopital above the equals sign. It's important to clue in the reader to the fact that you're applying L'Hopital's rule, because otherwise it might be hard to figure out what's going on if you weren't expecting it. And remember that to do that, we will take the derivative of the numerator. In this case, it's 2x. And we'll take the derivative of the denominator. The derivative of 1 is 0. Derivative of cosine is a negative sign. So we have negative sign. That is a positive sign. And we have sine x there. It's important to note that we have not used, we're not taking the derivative of the whole thing. This isn't quotient rule or anything. Taking the derivative of the whole thing wouldn't make sense, right? The limit of a function at a certain point, we do not expect to be the limit of its derivative. But as the textbook illustrates with some graphs, when we have a ratio of two functions, under certain circumstances, we expect the ratio of their derivatives to have the same limit. So we have this, and this is certainly simpler. If we plug in 0 here, we again have 0 over 0, which is indeterminate. We could use L'Hopital's rule a second time, and that will work here. But, again, it is nice to use more elementary methods when they exist. So let's divide numerator and denominator by x here. So we have 2 divided by sine x over x. And now we see as x approaches 0, sine x over x approaches 1, right? So this is 2 over 1, or 2. That is also what you would get if you applied L'Hopital's rule a second time, right? We could have alternatively, from this, done this again. We'd have 2 over cosine x. Plugging in 0, we get 2 over 1 equals 2. So that would work also. But again, L'Hopital's rule is, there's a lot of theory behind it, and it's, it depends on a lot of things, and it's a little bit fragile in certain ways. So we try not to use it more than necessary. But it is extremely useful in cases like this, where it would be much more difficult to try to work out the limit by other means. So let's take a look at number 22, which I should back up a little bit. One of the things that made this made L'Hopital's rule such a good choice here is the fact that we have the transcendental function of cosine together with this polynomial x squared, and it's a little bit difficult to find ways that those relate outside of those very specific trigonometric limits, right? We know that 1 minus cosine x or cosine minus 1 over x will approach 0 as x approaches 0. And we know sine x over x approaches 1 as x approaches 0. And that's the bulk of them, right? Other trigonometric expressions tend not to work out so well. So it's that kind of mixture that clues us into the idea of using L'Hopital's rule. If this were just a ratio of polynomials, it would be much preferred to use one of the techniques discussed in Chapter 2. Now with that in mind, number 22, without this natural log, we would just want to simplify this and work things out, but we do have a natural log and an x squared, which those don't seem to go together very nicely. Let's figure out what's happening here. As x approaches infinity, the square root of x approaches infinity, so the natural log of that approaches infinity, and x squared is approaching infinity, so we have an infinity over infinity indeterminate form. Just as with the 0 over 0, I'm just jotting this off to the side. I don't want to write equals infinity over infinity because this is not a number, right? The limit doesn't have that value. That doesn't make sense. This is just a notation to keep track of what's happening here. So coming back to this, let's again apply L'Hopital's rule. We have the limit as x approaches infinity of, I want to take the derivative of the numerator. So the derivative of the natural log of something is 1 over that thing. We have fractions and radicals, and we'll have fractional powers. So let me actually do this. This is x to the 1/2. So let's say that its reciprocal then is x to the negative 1/2. So that is the derivative of the natural log, but we have to use the chain rule to multiply by the derivative of what was inside there. The derivative of x to the 1/2 power is 1/2 x to the negative 1/2. This is all divided by the derivative of x squared is 2x. Now you see this is kind of a mess here. We need to figure out what's happening, so we should simplify. Let's see here, x to the negative 1/2 times x to the negative 1/2 is an x to the negative first, so we can bring that down here. Also that 1/2, bringing that 2 down, looks like we get 4x squared in the denominator underneath 1. And now when we see this, x is approaching infinity, so this denominator is approaching infinity, and 1 divided by increasingly large numbers approaches 0. So we find here that the limit actually is 0. Telling us basically that as x becomes large, x squared and the natural log of the square root of x both grow without bound, but x squared grows much faster. So that in the long run, this denominator becomes much larger than the numerator, and those ratios shrink down towards 0. Next, we have number 24. The limit as t approaches 0 of 8 to the t minus 5 to the t divided by t. Once more, we'll plug those in. When t approaches 0, we approach 8 to the 0, which is 1. 5 to the 0 is 1. And t is approaching 0. So that is 0 over 0. An indeterminate form. Once more, we want to take a moment to look to see if there's maybe any algebra we could do to simplify this, but these exponential expressions, 8 to the t and 5 to the t, they're different bases, so they don't interact well with each other, and they also don't interact well with the t that's down here. So once more, since we have a 0 over 0 indeterminate form, we will apply L'Hopital's rule. Taking the derivative of the numerator, that would be 8t times the natural log of 8 minus 5 to the t times the natural log of 5. I believe I misspoke there. I think I might have said 8t. I meant, of course, 8 to the t. 8 to the power of t there. We have these exponential functions. All divided by the derivative of the denominator, and the derivative of t is just 1. So this is nice. Now we can actually just do the substitution, right? We have 8 to the 0, natural log of 8, minus 5 to the 0, natural log of 5, divided by 1. 8 to the 0 and 5 to the 0 are 1. So we have natural log of 8 minus natural log of 5. This is the thing about these indeterminate forms, is they can really be literally anything, right? We've had just 3 examples so far. This one was 0 over 0, and the limit turned out to be 2. This one was an infinity over infinity indeterminate form whose limit turned out to be 0. And here we had another 0 over 0 indeterminate form, and that limit is the natural log of 8 minus natural log of 5. This is a perfectly good way to write this. Depending on your application, you might want to write it in some other way. For some purposes, it might be nice to have only a single logarithm, in which case you could use log properties to rewrite this as the natural log of 8/5. That would be another good way of writing that answer. This might also be useful if you're trying to estimate the size of this, right? Natural log of 8 and natural log of 5 are kind of hard to think about themselves. You kind of estimate those, but then you have to try to think their difference. What's that going to be? If you consider the natural log of 8/5, and you maybe ballpark the size of that, compare it to e, you might have a better job of figuring out about how big this is rather than one of the others. On the other hand, sometimes it is useful to make the argument of a natural log as simple as possible. Sort of like when we have a square root, for example, if you have square root of 12 and we want to simplify that, you find any perfect squares and pull those out, and you'll rewrite this as 2 radical 3. Even though 2 radical 3 might look a little more complex, the fact that we have less inside the radical, we call this simpler. Similarly, we sometimes want to simplify logarithms in a similar fashion. 8 is 2 cubed, so using log properties, we can write this as thrice the natural log of 2 minus the natural log of 5. That would be another way of writing this, where we have broken this up and made each logarithm as simple as possible. Like I say, this first one is perfectly fine as far as I'm concerned, but depending on your purposes, you might find it useful to combine them together into a single logarithm, or to break things down as far as possible. Any of those would be reasonable responses to this question. Let's see, that was the third one. Now we have number 26, the limit as u approaches infinity of e to the power of u over 10 divided by u cubed. Once more, let's come off to the side and figure this out. As u approaches infinity, we have infinity, well, I shouldn't say infinity over 10, that's a weird thing, but u over 10 will also approach infinity. So e to that power approaches infinity. And u cubed is approaching infinity, so this is an infinity over infinity indeterminate form. We always have to check these things. Don't assume just because you have a quotient that you can just dive right into L'Hopital's rule, because if it's not an indeterminate form, you'll get something completely wrong. I think there's an example in the textbook about that. Or if not, you can just go back to an old limit question from chapter 2, back when they were sometimes giving you things that direct substitution worked and didn't give you an indeterminate form. If you try L'Hopital's rule, you'll get a completely different answer, if you get any answer at all. So always check this before you do anything. So let's go ahead then and apply L'Hopital. The limit as u approaches infinity of taking the derivative of the numerator. This is a natural exponential function, so that'll be itself times the derivative of the exponent. The exponent is u over 10, and its derivative will be 1 over 10. So we have 1/10 e to the power of u over 10 divided by the derivative of the denominator is 3u squared. Let's simplify this a bit. This 1/10, of course, we can bring down into the denominator. We have e to the power of u over 10 divided by 30u squared. This has the same, a similar structure to what we started with, right? The numerator is still going to infinity. The denominator is also still going to infinity, maybe slightly less quickly because we have a u squared instead of a u cubed. But similar kind of thing. This is still an infinity over infinity indeterminate form. Let's apply L'Hopital's rule again. And once more, the reason we're having to use L'Hopital here is because we have an exponential function, which is transcendental, together with the polynomial function u cubed starting off, and then down here with the u squared. So, again, those don't work together very nicely, so we just sort of have to see what we can do. So we take the derivative of the numerator and get 1/10 e to the power of u over 10, and the derivative of the denominator, we have our 30 times 2u. So cleaning this up a little bit, we have e to the u over 10 divided by 600u, it looks like. All right. Well, we're getting somewhere. We see these numbers keep growing, which might be concerning to you, but also notice that the powers on u keep dropping. So we're almost there. This is still infinity over infinity, but one more step should do it for us. Once more, the derivative of that, we have 1/10 e to the u over 10. This is divided by 600. And if you want, you can simplify this, move this 1/10 down to make the 6,000 in the denominator, but we can see now all that's left is this e to the u over 10. That is approaching infinity. The 1/10, this is still approaching infinity, divided by 600, it's still approaching infinity. And we find that that limit is infinity, meaning that it grows without bound. That limit does not exist within the real number system, but it increases without bound. So this is not an uncommon sort of thing to happen, particularly with things like exponentials or certain kinds of trig functions. Repeatedly applying L'Hopital's rule might not change the transcendental part very much for some of those transcendental functions, but polynomials will drop in power each time you take their derivative. So depending on what you have, you might get into a situation like this where you just need to iteratively apply the rule a few times and pare things down and figure out what's happening. The fifth and final example I want to do here is the limit as x approaches infinity of the hyperbolic sine of x divided by the hyperbolic cosine of x. So we have to think about what these things mean, and if you come off to the side, and I'll remind you here, the hyperbolic sine and cosine are e to the x plus or minus e to the negative x divided by 2, right? Cosine will be plus because it's an even function, sine will be minus because it's an odd function. In either of these cases, as x approaches infinity, e to the negative x is approaching 0, e to the x is approaching infinity, so sinh over cosh has an infinity over infinity indeterminate form, right? So the natural thing to try might be to apply L'Hopital's rule. Limit as x approaches infinity of, well, the derivative of sinh is cosh, and the derivative of cosh is sinh. So we have this, and that still has infinity over infinity, and you probably see the problem here. You might try L'Hopital's rule again, but that's not going to achieve much, is it? Because the derivative of cosh is sinh, and the derivative of sinh is cosh. That gets us literally nowhere. This problem, we cannot directly apply L'Hopital's rule on. As I believe I mentioned in my written notes, and I'm sure the textbook has stressed as well, this is not some universal tool that takes care of all limits forever. It's just another tool in our toolbox to work with. We still need to have other techniques at our disposal. Let's go back to this definition that I have up here. Sinh x is e to the x minus e to the negative x divided by 2. Cosh x is, this is bad. I was talking about other things and not paying attention to what I was writing. I need to write the limit operator. We cannot forget that. It's very important. Otherwise, that is a completely false equation. So, hopefully you when you're working on your math, you won't be trying to talk about the things you're about to do, and you can instead focus on the things that you are doing. Okay, so for sinh x, we have e to the x minus e to the negative x over 2. For cosh x, we'll have e to the x plus e to the negative x over 2. Let's simplify that their fraction. These halves cancel. We have e to the x minus e to the negative x divided by e to the x plus e to the negative x. And now, looking at this, you can also see why L'Hopital's rule will not work, right? When we take derivatives, the e to the x stays the same. The e to the negative x term is just going to flip signs, so we just keep switching signs between positive and negative here. Instead, we need to do something else. What are we going to do? Well, let's think back to the techniques that we would use. This is a limit as x is approaching infinity. And thinking back to chapter 2, when we had a rational function and x was approaching infinity, we would try to divide out the highest power in the denominator, or equivalently multiply by its reciprocal. So let's try to get rid of this e to the x here by multiplying numerator and denominator by its reciprocal, e to the negative x. So we have the limit as x approaches infinity of e to the negative x times e to the x is 1. And e to the negative x times e to the negative x is e to the negative 2x. So we have that divided by, again, e to the negative x times e to the x is 1. We have plus, multiplying these, we have e to the negative 2x. And now we see, okay, as x approaches infinity, e to the negative 2x approaches 0. So this goes to 1 minus 0 over 1 minus 0, which is simply equal to 1. Okay. Not a very hard limit if we apply the chapter 2 techniques in this new situation. Right? This isn't exactly a polynomial, but we have a sum of sums and differences of terms, and we can tell which terms grow faster than the others. Right? The e to the x keeps growing, as opposed to the e to the negative x, which keeps approaching 0. So by using a similar technique to that, we are able to manipulate this into a form where then it's not exactly substitution because we have this infinity. It's not like we're plugging in infinity, but we can evaluate the limit term by term at this point. Those terms go to 0. And that simplifies pretty nicely. So again, just because you see an indeterminate form that you recognize, that does not automatically mean you should use L'Hopital. Take a moment to consider whether another approach would be better. If you don't see another approach immediately, like it's totally okay if you don't immediately think of this. Looking at something like this, L'Hopital's rule is a perfectly good thing to try, but pay attention to what you're doing and take a look at whether it's actually getting you anywhere. The textbook has another couple of exercises, I believe I called them out of my notes, that have other situations where L'Hopital doesn't really help us advance. So that is something to keep in mind. But for the most part, as you can see in these various examples, when we get either an infinity over infinity or a 0 over 0 indeterminate form when we're trying to evaluate a limit, and especially if it is not purely algebraic, like polynomials and radicals and things, particularly when you have transcendental functions thrown into the mix, trigonometry, logarithms, exponentials, L'Hopital's rule is often a good thing to try in such circumstances.